some calculations have been made. Suppose we have 0.04% phosphorus in steel. So, what is its impact on segregation? What is its impact on actual solidus during solidification? What is its impact on the relative depth of the solid shell and the relative thickness of the marshy zone? Let us try to understand these figures. Now, all these have been calculated. So, these are calculated values and those have been plotted. So, TSC is the equilibrium solidus, TL is the liquidus. So, with carbon how does it change? So, it is basically from the iron carbon diagram. Iron carbon diagram, if you look at it, how the liquidus temperature and the solidus temperature will change. So, that is one. TSA is the actual solidus, this is actual solidus. Here the effect of microsegregation has been put into account. So, TSE is the theoretical solidus which you get from equilibrium diagram, and TSA is the actual solidus which has been calculated based on microsegregation from modified shell equation. Now, at what stage of solidification do you calculate this? That is important, because this is this relative portion of the solidus, this actual solidus temperature, this will all depend on at what stage of solidification you are there. So, what has been done is we have used a casting speed of 1.5 meter per minute, 25 millimeter below the meniscus calculation has been done. At that point of time the solidification time was 1 second. So, this is the 25 millimeter below meniscus, and the shell, the solid shell thickness SM, the theoretical solid shell thickness is, as I have told you earlier, it depends on the capital K, which is the solidification constant, into time to the power 0.5. So, since time is 1 second and K, if you assume 2 millimeter per second to the power 0.05, so we can calculate the theoretical solid shell thickness, which is 2 millimeter. This is theoretical, but actually what is the situation? It depends on the level of microsegregation. Now, the effect of 0.04% phosphorus. I have told you phosphorus is very deleterious. In steel, if you have 0.04% phosphorus, which is relatively high, we should not have so much of phosphorus in steel, but for calculation purpose we have taken 0.04% phosphorus. Then let us see what happens. The actual solidus, as I have told you, it also depends on what is the mode of solidification. As you are going from delta to gamma mode of solidification, that means when you are going to more amount of carbon, which is you will be having a delta mode, austenitic mode of solidification, you will find that the effect of microsegregation is quite high. Look at this figure, TSA. Because of microsegregation, the equilibrium solidus is coming down when here, that means around 0.1% carbon, where microsegregation is relatively less, it comes down by only about say 20 degrees centigrade. But you come to a level of say 0.2, 0.25, 0.3, here the depth, the difference is almost 100 degrees centigrade. So, from a level of 20 degree it is increasing to a distance of 100 degree, that is one. And number two, what is its impact on the relative depth of solid shell and marshy zone during solidification? That is again important. I have told you 2 millimeter is the equilibrium solid shell thickness, but in reality look at the figures. At 0.1, when segregation is minimum, the solid shell is quite thick, it is about 1.5 millimeter. So, that means from the theoretical value it is not much less, but look at this carbon concentrations 0.25, 0.3. So, here the solid shell is very thin, is hardly 0.2 millimeter. That means only 10% of the theoretical solid shell is actually solid, and the rest is what? Rest is mushy zone, because mushy zone and the solid, this together will constitute the, and of course liquid is there. So, the actual solid shell becoming thinner means mushy zone becoming thicker, the depth of mushy zone is more. So, what is the implication of this? Implication is the strength of the strand. If the strand during solidification, the solid shell is thinner and the mushy zone is thicker, so the strand is having very small amount of solid during solidification, the strength is consequently relatively low. So, this is the implication of segregation, microsegregation of alloying elements on the impact, on their impact on the strength of the strand, solidifying strand during the stage of solidification. So, this is very important. We have to remember what is the impact of phosphorus. We had shown here that phosphorus, the values are relatively less. It is slightly higher compared to sulfur, but sulfur, because of manganese, the deleterious effect is taken care of to a large extent, but for phosphorus there is no element which can take care of it. So, low phosphorus is essential, particularly for gamma solidification. Look at gamma and delta. For delta solidification, the value of small k is 0.23, but for gamma solidification it is 0.13. So, it is still lower. So, in case of gamma solidification, that means when we are going to higher and higher carbon, any steel which is having more amount of carbon, we have to be more careful about the phosphorus, because the extent of microsegregation will be more for gamma solidification. So, phosphorus have to be less, then only the effect of microsegregation will be relatively lesser. So, we have to remember what is the role of phosphorus, why it is harmful, why it is deleterious in causing microsegregation, and if there is microsegregation, I have calculated the different values, the actual solidus, to what extent it is coming down from the equilibrium solidus, and if this is coming down means the difference between TL and TSA, and then this depth of this depth, that means the solidification range becomes quite wide. If solidification range becomes wide means the mushy zone will become wider, and this difference between the surface temperature of the solid and the actual solidus, this difference becomes less. This difference is quite more. You look at this figure, is quite more at 0.1% carbon. So, at 0.1% carbon, the solid shell is relatively thick and the mushy zone is relatively thin, but as you are going to high carbon levels more than 0.2, what is happening? The actual solidus is coming down. So, the temperature interval is increasing, temperature interval between liquidus and actual solidus. This temperature interval was relatively less for 0.1% carbon, but for 0.2, 0.3, 0.4, here you see the depth, the difference between the TL liquidus and the actual solidus is quite high, and the difference is quite high means the mushy zone will be quite wide, the depth of mushy zone is wide and the solid shell is very thin. So, if the solid shell is thin, look at this figure, the solid shell thickness at a just depth of say 2 millimeter, at a depth of say 1 millimeter or 2 millimeter, at a depth of 25 millimeter, 25 millimeter below meniscus, at this depth, what is the solid shell thickness? It is very, very small. So, the strand will have much less strength because the solid shell is less, mushy zone is quite deep. So, the shell strength is also less. So, segregation, heavy amount of segregation is what is it creating? It is creating first lower solidus temperature. So, what is the consequence of this? If the solidus temperature comes down, the temperature interval for solidification between liquidus and an actual solidus, this increases. Say at 0.1% this is relatively less, and 0.3% it is quite high. So because of this, because of the suppression of the actual solidus, what is the consequence? Consequence is the marshy zone is quite deep. I think I have discussed this earlier. If the actual solidus temperature, this comes down, the difference between the liquidus and the actual solidus increases. If this increases, the depth of this also will increase. This is directly proportional. The marshy zone depth is related to the temperature interval between liquidus and actual solidus. So segregation, particularly say phosphorus, if the higher amount of phosphorus you have, there will be too much of segregation. Because of that, the actual solidus will be suppressed, will be depressed rather, will come down. So the difference between the liquidus and the actual solidus will increase, and because of this, marshy zone depth will become quite wide, and if this decreases, so this temperature interval is becoming lower, the solid shell is becoming relatively thinner. This is what has been shown here, actual calculation. At 0.1% carbon, solid shell is relatively more. Why? Because the temperature interval between the surface of the solid and the actual solidus is quite high, and the temperature interval of solidification, that means between the liquidus and the actual solidus, is relatively less. This difference is less, this difference is more. Because of this, if difference is more, means the solid shell will be more deep, and if this difference is relatively less, the marshy zone depth will be relatively less. So at 0.1% carbon, you see what is happening. Solid shell is relatively more deep, marshy zone is quite less deep. But look at what is happening here, 0.2 to 0.3% carbon. The actual solidus has been depressed because of microsegregation, because of austenitic solidification. So the temperature interval between the liquidus and the actual solidus is quite high, and the temperature interval between the surface of the solid and the actual solidus is quite low. This is quite low, this is quite big, quite large. So the depth of the marshy zone is quite big, and the solid shell is quite thin. This is the consequence of high segregation of phosphorus. All alloying elements will contribute their part in segregation. So it depends what are the small k values, what are the their diffusion coefficient in the solid. So all these factors will finally give us a relative amount of microsegregation, relative amount of segregation of the alloying elements. It depends exclusively on the small value of k. Small value of k is very important. Small value of k means more segregation. Small value of k in gamma solidification, you see gamma solidification, these k values are less. So that means the segregation of sulfur phosphorus will be more for gamma solidification. As such values are low, whether it is delta or gamma, and between delta and gamma, gamma again are low. Gamma values are again are low. But as I have told you, there is a savior for sulfur. Manganese is the savior. Manganese can help reduce the effect of the bad effect of segregation of sulfur, because it combines with manganese, it combines with sulfur forming manganese sulfide, and iron sulfide cannot form, because iron sulfide is the culprit that creates lower solidification temperature. So if you do not have manganese, then sulfur will pose a problem. If you do not have adequate amount of manganese, sulfur will pose a problem. But since there is no such savior for phosphorus, unfortunately, so phosphorus value as such has to be low, so that segregation effect is relatively less. Here the quantitatively some calculations have been done just to show what is the level of impact of phosphorus. How does it affect the actual solidus temperature? How does it affect the solid shell thickness during the course of solidification for different level of carbon? Different level of carbon basically indicates different solidification mode that I have explained earlier in the last discussion. So all these are related. How the alloying elements are controlling the solidification mode? They are controlling by controlling the carbon equivalent. In plain carbon steel, that means steels which have just carbon, iron carbon diagram is the criteria. In low alloy steels, we have to calculate carbon equivalent. That means how the alloying elements like manganese, silicon, chromium, nickel, whatever are there present there, small amount in low alloy steels, how they are affecting the carbon activity in solidification. So that will have impact on the carbon equivalent. So carbon equivalent, if we calculate depending on the chemistry of the steel, so then we know how the steel will solidify, whether through delta or through gamma or in a mixed solidification mode, at what temperature the solidification is complete. So these are all important. These are all important issues to understand what will be the impact on steel quality. Because why I am again and again repeating, more is the segregation, lower is the TSA, that means the actual solidus temperature is lowered due to segregation. More segregation means this value will be lowered further, and if this is lowered, the temperature interval for solidification increases, temperature difference between the liquidus and the actual solidus increases. As such, it increases with normal carbon, from equilibrium, iron carbon equilibrium diagram you can find out, but due to other alloying elements presence, due to microsegregation, all alloying elements will cause suppression of actual solidus. The actual solidus will be lower compared to the equilibrium solidus, but the carbon concentration, the mode of solidification will tell us what is that extent, quantitatively what is the extent. At 0.1% carbon, the effect of microsegregation is minimum, but at 0.3% carbon, 0.25, 0.3, 0.4, it is quite big, quite large. So the solid shell thickness is highest for 0.1% carbon and relatively lower for 0.25, 0.3, 0.4% carbon. This is very important to remember. So 0.1% carbon microsegregation is relatively less, solid shell during solidification is relatively thick, Marshy zone is relatively thin, but for higher carbons say 0.25, 0.3, 0.4, 0.5, just the reverse is true. The actual solidus is much lower, so the temperature interval for solidification is much higher. Because of this, the solid shell is quite thin and the Marshy zone is quite thick. So this has large implication, large consequence on what is the strength of the shell, strength of the solidifying strand, that is important to understand. Here at a particular level calculations have been made. So similarly calculations can be made at different level, different stage of solidification. So we can know what is the extent of solidification. It is possible to calculate. This I have explained to you how the different temperatures, that means particularly the actual solidus temperature, has influence on the depth of Marshy zone and the thickness of the solid shell. The lower is the value of actual solidus, this temperature interval between liquidus and actual solidus will increase. Lower this value, lower the actual solidus means TL remaining more or less constant, more will be this value. More will be this value means the Marshy zone also will be more. So that is why I am again and again mentioning the effect of microsegregation is to not only create a zone of higher segregation, that means the area which is solidifying at the last, which will have more segregation. That is number one impact. Number two, an equally important impact is the marshy zone depth is increasing and the solid shell thickness is decreasing. TSA decreasing means this depth is increasing, TSA decreasing means the difference between TSA and T0, that means the surface temperature of a solid, this is decreasing. So, solid shell thickness is decreasing, marshy zone depth is increasing because of segregation. So, this we have to remember what is its impact on the quality. Now, I will just start the discussion in today, the strength and toughness of solid shell, why this is important. Solidifying shell undergoes strain during and after solidification, we have to remember. Thus, when solidification is taking place, first whether solid shell is delta or gamma, that is important. Why it is important? Because the strength and toughness of delta and gamma at high temperature are not identical, they are different. So, what is the solid shell? Is it delta ferrite or austenite? That is important first. Also, the solid shell is undergoing lot of strain. Now, what are the strains? Let us try to see. During solidification, there is a ferrostatic force from the liquid during solidification. Ferrostatic force is from the liquid which is still there during solidification. After solidification, there is no liquid, there is no ferrostatic force. But during solidification, there is a lot of liquid. So, ferrostatic force from the liquid will push the solid shell. So, you on the solid shell you have some force acting on it, it will try to push the solid shell towards the mold, the direction is also known, ferrostatic force. So, there is some strain on it, number one. Number two, shrinkage due to solidification. First, whenever there is a solidification, there is a shrinkage, there is a volume change. Due to volume change, there is a density change. So, there is a volume change, there is a, that is why there is a shrinkage. Lower volume means there is a shrinkage. So, due to shrinkage, again there will be a force on the solid shell, number one. Again, if there is a transformation from delta to gamma, that means initially delta is forming and then delta is transforming to gamma, then this transformation to delta to gamma also causes transformation stress, strain. So, due to shrinkage, liquid to solid, whether delta or gamma, there is a strain, shrinkage strain. Then if the transformation takes place initially to delta and then to gamma, then where this transformation takes place, again this is important, this I will come to you later. So, because of this transformation there is again a strain. So, initially there was a ferrostatic force from the liquid, then during solidification again there is a shrinkage and there is a transformation. If there is a transformation from delta to gamma depending on a particular chemistry, again there is a shrinkage and there is a strain. Now, there can be mechanical strain due to bending and unbending of strand. This I have explained to you earlier, that whenever there is a bending of the shell, first the strand is coming out vertically from the mold, if the mold is vertical. If you are using vertical mold, the strand, solidifying strand is coming out vertically, but it has to be made horizontal finally. So, how it is made? So, first if there is a vertical mold, the strand has to be initially given a bending, and then there has to be unbending. These two combination will make the strand horizontal. So, because of this bending and unbending, the solid shell, solid portion of the shell will have some strain on it because of bending. The inner radius, the shell at the inner radius will have something, the shell at the outer radius will have just the reverse. If one is tensile, the other will be compressive. So, if there is bending, there is something strain, if there is unbending, there is again the reverse strain. Now, for a curved mold, you need not bend the strain when it is coming out, because it is already coming out with an angle. So, you need not bend it, but it is necessary to unbend it, to unbend the strand to make it horizontal, otherwise it will go on like a circle, which we cannot allow. The strand has to be made finally horizontal, so that we can take the cast product, we can cut that cast product. So, this is a necessity. So, if you have a carved mold, only unbending is necessary. So, during unbending again there will be some strand, there will be some strain on the solid shell, at the inner radius something, at the outer radius something. I have discussed earlier this. So, what I am trying to tell here is the mechanical strain. This is a mechanical strain due to bending and unbending of strand. So, these are strain because of shrinkage, solidifications, strain because of transformation, ferrostatic force, strain because of ferrostatic reaction. Now, there can be a thermal strain during secondary cooling. After the strand comes out from the mold, you have to use water for secondary cooling. Water is impinged on the strand surface, both at the inner radius and the outer radius. You must spray water or air mist. So, because of that there is a thermal strain. Why? The surface is exposed, that the surface is cooled relatively more, the interior is hot. So, because of temperature difference due to the secondary cooling, there is a thermal strain. So, you can make out so many strains are operating on the solid shell, on the strand, unlike ingot casting. So, that is why during continuous casting we have to be more careful about these strains. We have to be more careful about the strength and toughness of the solid shell. So, that is why what I am telling here is, look at it, the solid shell, whether it is delta or gamma, after solidification is complete, what is the constituent? Is it delta ferrite or gamma? This must have adequate strength and toughness at high temperature to withstand the different strains. High temperature, basically what I mean, during solidification and at temperature lower than solidification also. That is why what is important is to understand the strength and toughness of the solid shell at this temperature interval at 1400 degrees centigrade. The solidification is more or less, you see, at depend on the chemistry when the solidification will be complete. So, say low carbon solidification is relatively complete at 1400 degrees centigrade. At higher carbon solidification will be complete only at still lower temperature, solidification continues. So, what is important is from 1400 to as low as 600 degrees centigrade. Why this is important? Because when solid has already formed, then also the shell strength is important, because lot of strength and toughness is important, because lot of strains are created. So, the solid shell has to withstand those strains, otherwise there will be crack formation, there will be a formation of some defects if the shell cannot withstand these strains. So, this understanding of strength and toughness at high temperature is very important to control formation of crack in solid shell. Solid shell should have adequate strength and toughness. During solidification, as I have told you, the mode of solidification, the chemistry, the extent of segregation will determine what is the actual thickness of solid shell. So, during solidification, solid shell thickness you can get from segregation, extent of segregation. But after solidification, that means when the solid shell is 100%, you do not have any liquid, you do not have any marshy zone. So, there also the strength of the shell is important, solid shells, toughness of the shell is important, because if the strength is there, but if there is no toughness at particular, I will come to it later on, at particular temperature ranges the toughness is relatively low, we call it brittleness at certain temperatures. If it is so if there are strain on the shell, that means there can be formation of crack. So, it has to be understood very clearly that at what temperature, what is the constituent of the solid, whether it is delta or gamma, and what is the strength and toughness of the solid at different temperatures, so that whatever strains are generating, are getting created, getting impinged on the solid shell, whether the solid shell is capable of withstanding those strains. It is very important to understand that. If it can withstand, there will be no crack. The continuous cast product will be devoid of any defect, no crack formation. But if it cannot, if the solid shell cannot withstand some of the strains, whether it is ferrostatic, whether it is shrinkage, whether it is mechanical strain, thermal strain, they are getting created at different temperature zone. All are not, valid at all temperature zone. So at different temperature zones, different strains are getting created. For example, ferrostatic force, it is valid only till solidification. After solidification, it is no longer there. Then solidification shrinkage, it is valid only during solidification. After solidification, then there is no solidification shrinkage. This transformation to delta to gamma, it depends. This shrinkage from delta to gamma will be effective depending on when it is taking place, whether during solidification or after solidification. That is very important. Then mechanical strain due to bending and unbending, I have told you, it again depends on at a certain location in the caster. That means at a certain depth in the caster. Consequently, that means at certain temperature interval in the solid shell. So it is very important to understand at what temperature interval you are using bending and unbending, whether the strain, mechanical strain that is getting generated, whether the shell can withstand that strain, or there will be some crack formation. There may be bulging crack, there may be other crack. So this is very important to understand. And then the solid shell, whether it is delta or gamma, they have adequate strength and toughness at high temperature. High temperature means temperature from say 1400 to 1600. It must have adequate strength and toughness, then only it can withstand the different strains getting generated at different temperatures. So that the from the depth, suppose you have cast a solid steel say, and at the at the intersection, if you look at the intersection, you will find at certain depth there is some crack. So why does it form at certain depth? Because whether it formed during solidification, whether it has formed after solidification, solidification was complete, but then because of the mechanical strain due to bending or unbending, those cracks have formed. It is important to understand from the crack what is the type of crack, whether it has formed during solidification, at what stage of solidification, or after solidification. This is important. So thank you very much.